some other name. I don't know. What shall I call it? I mean, the 5 is one of the index, so I don't want to put 5 here, right?
Gamma.
Gamma. Just gamma, without any. Okay, just gamma. Okay, gamma, without any index. Call that. Actually, let me just call 2n plus 1. Okay? 2n plus 1. Okay. Again, there will be some I factors and so on, but that numbers, that's not, I'm not worrying about. If I look at this, then this is exactly the same property. So if I take gamma 2n plus 1 and multiply by, say, gamma 1, this side, okay, well, and look at the other guy, gamma 2n plus 1, gamma 1, like compare the two things. When gamma 1, when I multiply here, well, gamma 1 square is 1, right? From the anti-commutation relation, gamma 1 square is 1. From this relation, if I put I equal to j, this is gamma 1 anti-commutator is just 2 gamma 1 square. So 2 gamma 1 square is 2, so gamma 1 square is 1. Okay? So gamma 1 multiplying this side is 1. But when you multiply gamma 1 from that side, I have to move it step by step until it reaches here, right? But every time I move across, I pick up a minus sign from this relation, right? How many times I have to move across? It's an odd number of steps I have to move across, right? So I'll have a minus 1 to some odd number, which is minus. So by the time I come here, I will get a minus, and then gamma 1 square will go out, so you'll get back again. So this and this have opposite sign, right? So it is this guy which is equal to 0. So the anti-commutator, which is 1. Okay. This is the property. Now, if I apply, let me see how to see that. Yeah. I mean, so suppose I apply gamma 2n plus 1, gamma 2n plus 1 on these states. You see, all of these guys have the same sign, right? Because, how to say this? See, what I want to show, what I want to say is that all the even guys come with one sign of gamma and 2n plus 1, and all the odd guys come with another sign, opposite sign. Let me see how to say this. Yeah, you could say it the following way. So let's suppose I chose, say one of this state I chose of some value, gamma 2n plus 1 has, say, some eigenvalue 1, plus 1. Choose plus 1. Okay. So suppose I started with this. One state is gamma 2n plus 1 is 1. Then if I apply gamma 2n plus 1 on this, okay, what am I going to get? I move this gamma 2n plus 1 here. I pick up a minus sign. Then gamma 2n plus 1 acts here, it gives you a minus sign. Okay? So if gamma 2n plus 1, so I'm just writing down the eigenvalue of gamma 2n plus 1. If I pick up this eigenvalue plus 1, then this eigenvalue will be minus 1. Okay? This one will be again plus 1, because when I move gamma 2n plus 1 across 2, I have to move it 2 times with the same sign. So all the even guys have the same sign, and all the odd guys have the same sign. I mean, opposite to the even ones.
Are this relation also valid for the bigger gamma matrices?
Yeah, but these are linear in gammas, right? Because these are going to be some combination, right? Gamma 2i minus 1 plus gamma 2i plus 2i, no? Plus I gamma 2i. But the point is how many gammas are there? Yeah, sure, right?
But in a sequence, we don't have all the gammas from 1 to 2i in that sequence. We go
no. What I'm saying is I multiply this equation by gamma 2n plus 1. Sorry, small gamma 2n plus 1. This is small gamma 2n plus 1. I mean, I have not defined capital gamma 2. Yeah, sorry. So small gamma 2n plus 1. And then re-express that in terms of small gammas. But the important point is that the odd guys will have odd number of gammas, and even guys will have even number of gammas, right? Small gammas. So in one case, when you move it across, it picks up a minus sign. In other case, it picks up plus sign. So these two guys have opposite chiralities. So that's what is happening. So this way we are constructing. Oh, I should now. So the actual dimension of the representation is half times. Irreducible representation is that. That is irreducible representation. But there are two chiralities. There are two chiralities. And incidentally, this since we discussed the Dynkin diagrams, the Dynkin diagram of the, I didn't explain anything, but I just told you that for SO2n, I just mentioned that to you. Without giving any proof or anything like that. The rank is n. Cartan subalgebra is n dimensional. So it will have n points, and the diagram is like this. So 1, 2, 3. So the last one. So this is that. So let's say this is the nth guy. This is n minus 1th guy. This is n minus 2th guy, and this is the first guy. I'm just labeling alpha 1, alpha 2, alpha 3, alpha n minus 2. No? Just calling that. So this is a peculiar thing here, n minus. Now, I told you also that any irreducible representation I can define by just specifying non-negative integers to each simple root, right? So, these are all, each of these dots, each of these circles represent a simple root. Okay? So, for example, there will be one representation. Let me remove that. For the one representation would be, I put 1 here and everything else 0. Everywhere else. The thing is that non-negative integers, it could be 0. So what it tells you is that the highest weight state is the highest weight state with respect to all the SU2 subalgebras, because each circle represents an SU2 subalgebra. Every x alpha gives you an SU2 subalgebra. So our highest weight state is the highest weight with respect to each of these SU2 subalgebras. But this is a spin 0 representation for all of them, and spin half representation for that SU2. Okay? That's what it means. The highest weight. But then of course you have to, it's not so simple, it's not a direct sum of SU2 subalgebras. It's a complicated algebra, right? You have to apply all of that. And this way, when you do this, you just get the 2n dimensional representation. This is what is called the vector representation. After all, SO2n was a rotation in a 2n dimensional vector space. So surely there's a 2n dimensional representation, the defining representation, right? That's that. Now, if you take 0, 1, 0, that is the adjoint representation, okay? And so on. But what is interesting is this guy. If you take this one here, that is one of these spinor representations. Okay? 1 here and 0 here. But you could have also chosen other possibilities, 0 here and 1. So that's the difference between these two. There's a complete symmetry here, you see. If you flip, nothing changes, right? But these two representations are exactly the two spinor and anti-spinor representation. The difference between this and that is that just the gamma 2n plus 1 action. So these are the two spinor representations in SO2n. Since I cannot stop myself from saying this is an amazing thing. You see, this is 2n, right? This is general for 2n. But we said this was if I label this as the first root, second root. This is not the numbers I'm writing. It's not the highest weight. These are just labeling the root. So this is alpha 1, alpha 2. This is alpha n minus 2, alpha n minus 1, and alpha n. Right? Now, if I take n equal to 4, which means SO8, because SO2n, right? SO2n. So if I take SO8, so n goes from 1, 2, 3, 4, right? So there will be only 4 dots, 4 circles. In this case, this diagram just reduces to that. Okay. So this is quite amazing, right? Because here you have only a symmetry of a flip like this. Huh? Here you have several, and you can flip this, you can flip that, you can flip this, right? But you remember, when I had the 1, 0, 0, 0, that was a vector representation. When I have 1, 0, 0, 0, it's a spinor representation with one chirality. And when I have 0, 0, 0, 1 is an anti-chiral spinor representation. But here there is a complete symmetry. I can flip this, I can flip that. That means the vector representation and the spinor representations, you can go from one to other by this flip. This is what is called a triality. Okay. And I should say that the superstring exists because of that. Superstring exists precisely for this reason. Exists meaning mathematically. I don't mean nature. I mean as a consistent logical system. It exists for this reason. This triality. It's a very peculiar thing. This happens only for SOA. Nothing nowhere else. Just a peculiar thing. Finally, the last comment. Last comment. This was for E1, SO2n. You can ask the question: what happens to odd SO2n plus 1? Okay. Well, it's the same dimension because you see that's why I call gamma 2n plus 1. I have already the gamma 2n plus 1, which satisfies now. I mean, because anyway, the gamma I, gamma j, anyway satisfied 2 delta ij, right? The gamma 2n plus 1 with gamma I, gamma I, was 0 by construction. Okay? And finally, all that is left over is to look at gamma 2n plus 1 square. That should be equal to 1. But that you can normalize it. You can put some appropriate number here to normalize it. Okay? I or whatever to make it. So we obtain already for free the Clifford algebra for the odd guys from the even guys. Right? So this means the dimension of this representation is for the SO2n plus 1 is 2 to the n. Okay, because these were all 2 to the n by 2 to the n matrices. Correct? These are all 2 to the n by 2 to the n matrices, where gamma 2n plus 1 was of this form plus and minus, plus 1 and minus 1, where this is a guy for the even levels, and this was for the odd levels. Right? So now we have this big algebra of the SO2n plus 1, where we had the original gamma matrices, and together with that I add this gamma matrix. So the dimension of this representation is 2 to the n. And there is no concept of chirality here, because I mean you have both chiralities at the same time. I mean, for the 2n dimension there is the 2 chiralities. In odd dimension there is no concept of chirality. Okay. So this is the shot. Yeah. Okay, I think I must make a move soon. So I would suggest, I mean, there will be a tutorial this Friday. And not the next week. Next week you'll be busy with preparing for RQM, right? And then maybe the week after, one of the days, maybe Wednesday, we could meet. After you have some chance to go through the thing, so that you know what doubts you have, no? What questions you have. And we can meet for 1 or 2 hours and discuss here. I mean, I don't know, how will we know? Should we fix already some time? Or how about 2 o'clock? I'll meet. Probably there are no lectures anyway, right? So I'll check with Patricia if this room is available. Okay.